Each time a router processes a packet, it decreases the time to live by 1. And when that value gets down to 0, it discards the packet, effectively ending the loop. The default time to live for macOS and Linux is usually 64 hops, and the default time to live for Windows is 128 hops. Since the router is decreasing the time to live by 1 each time the packet goes through, it's watching that number decrease every time it goes through a looped connection. And when the time to live gets to 0, the router drops that particular packet. If we were to look at the frame of IP, you can see there's version numbers, header length, type of service, total length, and other fields within the IPv4 header. The one we're interested in is the one called time to live, and that's the one that the router will use to determine if it's gotten down to 0 and if it should discard this packet from the network. Here's a very simple protocol decode of an IP header. You can see this is frame 1. We have the Ethernet information, what the MAC address is for the source MAC address and the destination MAC address, and this is an IP version 4 header. You can see the source IP address and the destination IP address in the header itself. If we were to break this header open and look at those individual fields that we mentioned from that previous slide, you can see there is a differentiated services field, a total length field, an identification field, and right here is a time to live field. The time to live for this particular packet is 58 hops. So this packet would need to go through 58 more routers until this got down to 0, at which point it would be removed from the network. In most cases, our total number of hops between us and the destination that we're trying to visit somewhere on the internet is usually around 12 to 16 hops, sometimes more and sometimes less. But that's a relatively small number when you consider that the total default time to live on macOS or Linux is 64 hops and the default on Windows is 128 hops. That gives us plenty of room to be able to get data from one side of the internet to the other and not have that information accidentally dropped by a router. Depending on the protocol you're using, time to live may have a different definition. With routers, time to live is associated with the number of hops. But in DNS, or the domain name system, the time to live is associated with the total number of seconds. Let's take a scenario where we're performing a DNS lookup, and you can do this yourself by using NSLookup or DIG, and you can resolve or look for the device www.professormesser.com. And your DNS server will return some type of IP address associated with the Professor Messer web server. Inside of that DNS resolution is information about time to live. This tells us how long we should cache this local entry on our system. So if we want to cache it for a certain number of seconds. How many seconds? Well, we're going to cache it for the time to live seconds. The time to live is included with the configuration on a DNS server, and this is the output from the command dig www.professormesser.com. You can see that the answer section, where the DNS server is providing us information, says that the server www.professormesser.com has a time to live of 300. This is an internet address. The A is for address. And then we have 3 different IP addresses associated with my web server. This 300 value is the one telling our local machine, keep this IP address in your cache for 300 seconds. If you do the math, that is 5 minutes. Once that 5 minutes has elapsed, our local cache removes that particular resolution. And if you want to know the IP address for that same server, you would need to perform another DNS query to update your cache for another 5 minutes. This allows me, as the administrator of my web server, to be able to change the IP address in my DNS configuration, and I can feel relatively secure that most people will have an updated version of that IP address within 5 minutes. We use time to live for many other protocols as well, so make sure you look at the documentation for that protocol to understand exactly how we're measuring time to live for that particular protocol. Cloud computing has undeniably changed the way we approach technology. With one click of a button, we can deploy an application and multiple services, all seemingly with unlimited resources. We're able to scale up and scale down these applications as we need, providing elasticity, especially in times when we have large demand, and then scale it back down when that demand goes away. We also have applications that we can now scale up or scale down and access those applications from anywhere in the world. Cloud computing also uses multi-tenancy, where many different customers are using the same cloud infrastructure. This allows for efficiency in the use of technology and efficiency in how much it costs to use this technology. Not only do we have virtual servers that can live in that cloud computing infrastructure, we can also have virtual networks. Let's take the scenario where we might have 100 individual servers that are running in our data center. That's a relatively large farm of servers. We've designed this infrastructure to have redundancy in the network. There are multiple servers. We've got load balancers and multiple firewalls, and we've designed it for uptime and availability. But now let's take this entire physical infrastructure and let's move this infrastructure to the cloud. We're going to migrate 100 physical servers to effectively one very large physical server. Inside that one very large physical server, we will run 100 virtual servers inside of it. Now that we've taken these 100 physical servers and migrated them to a cloud infrastructure, what do we do with our networking infrastructure? Not surprisingly, we will virtualize this network infrastructure as well. This is referred to as Network Function Virtualization, or NFV, where we can replace our routers and our switches and our other networking devices with virtual versions of those networking devices that are running in this virtualized environment. Although our firewall and our switches and our routers are no longer physical, they still have the same functionality. We can see those devices, our network